Hello everyone, and welcome to our webinar titled What's New in Geomatica and GXL 2018. This is Kevin Jones at PCI Geomatics, and we're really pleased to be here with you today. We'll be giving you an overview of our new and updated technology for 2018. So just a few logistics to get out of the way. The lines are all muted by default, so if you want to interact with us, which we really want you to do, we strongly encourage you to use the chat function in the interface. You can also raise your hand if you're having any kind of a problem, or if you would like us to unmute your line, perhaps during the Q&A session at the end, we'd be happy to unmute your line, but you'll have to let us know either through the chat or by raising your hand. Today's presenters are myself on the left, Kevin Jones, Director of Marketing, PCI Geomatics, and joining me is Jason Flatt, who is one of our technical solutions specialists. And he'll be showing you a preview of a webinar that he'll be doing in more detail in a couple of weeks, which is going to be SAR-based object image analysis. This webinar is the first in a series of webinars that we'll be providing over the coming weeks. The goal today is to give you a little bit of an overview of what's new within the technology, and then over the few weeks you'll actually have an opportunity to come back and walk through in detail the different parts of the technology that we're presenting today. So today we'll be showing you a little bit of an overview and giving you a taste of what's possible with the new version of Geomatica, which you can download at any time, and then we'll come back and we'll review things in detail. The very first one that's going to be coming up is a case study of using multi-temporal RadarSat-2 imagery for wetland mapping, which combines the use of object-based image analysis with radar data. So that's the one that we'll be doing on December 11th, and we'll have some more information on how to register for that one coming up towards the end of the webinar. And we have some other topics coming up: DSM True Ortho, InSAR processing, multi-sensor mosaicing, and analysis-ready data tools. So we'll get into those. You'll get a sense of what those are all about as we get through the presentation. So first of all, we'd like to introduce, if you haven't seen yet, the new graphics that we've put into our software, and also the information that this communicates. Quite a information-rich graphic that we've put into our release for this year. And I'll just spend a few moments kind of explaining what this is all about. With the 2018 technology, both for Geomatica and GXL, we've really chosen to focus our attention on a key trend in Earth observation, which is multi-temporal analysis. And what you see here is essentially a location which is near and dear to our hearts, being an Ontario, Canada-based company. This is a location known as Algonquin Park. And Algonquin Park is an interesting location. It actually has a combination of recreational use and industrial use, and they exist together successfully. And so monitoring resources through the use of multi-temporal imagery is a key policy objective for people like the government of Ontario. And the use of remote sensing technology and Earth observation technology is key to doing that. So what this graphic represents is multi-temporal imagery collected over multiple years, and how that imagery can be used to derive information. And what we see in the two circles are basically active deforestation or active logging and reforestation activities over a particular location within proximity to a park, camping site basically, or campgrounds. So we're really excited with this release to present technology that we've developed that really is going to help you perform multi-temporal analysis with this version, and going forward even more with degrees of automation as we go forward with our next versions. There's three key things that are part of this release that we'd like to talk about today. The first one being analysis-ready data tools. And this relates to the concept of multi-temporal analysis. So as you likely know, the multi-temporal analysis is essentially a fancy way of saying that we're doing change detection. And change detection is reliant upon data being prepared in such a way that it is easily consumable and can produce scientifically rigorous results. And so a term has been coined within the industry over the last year and a half, which is known as analysis-ready data. And what that means is the data has been pre-processed so that when you compare images of the same location over time, you're measuring what's occurring on the ground as opposed to what's happened in processing of the data. So we'll spend a little bit of time talking about that, but that is a key concept and a key theme that's part of our 2018 software release. A second key theme or key area where we've added new technology is aerial production. So everything to do with producing ortho mosaics from aerial imagery and satellite imagery, but very much a focus on high resolution aerial data sets with this release, with the introduction of the semi-global matching and many productivity automation, productivity enhancement and efficiencies in the software to enable aerial production to be very, very efficient. So we'll spend some time talking about that. And then we'll talk about some other productivity and automation enhancements that have been added to the software, including areas around object-based image analysis, InSAR, and mosaicing primarily. So there's always many areas where we improve productivity and automation in our software, but I just want to bring to your attention some of those key areas where we really have added some additional functionality in this particular version. So turning our attention now to the first topic, which is analysis-ready data tools. When we talk about analysis-ready data, we're speaking in the context of multi-temporal analysis. And if we're talking about multi-temporal analysis, we need to perform time series. And time series analysis is if we think about a system that will allow you to perform accurate, rigorous scientific measurements over time over the same geospatial area, we basically need to think about three key pillars that are required for that. So the first pillar that we see is the ability to generate analysis-ready data, or ARD. And ARD for us breaks down into two components. The first component is image alignment. So if you're comparing an image over a particular location and you're collecting an image from either the same sensor at a different viewing angle or a different sensor over the same location, you inevitably will have small shifts between your data. So we have developed technology that really allows you to bring all of your data into common alignment. The other part of the ARD creation component is to normalize your data from a radiometric point of view. So if we think about optical data, or radar data for that matter, we need to take into account differences in atmospheric conditions or differences in how the data was collected over time over the same location. So we need to remove atmospheric effects. We need to remove anything that isn't directly related to the surface reflectance on the ground. So radiometric normalization is all about producing data that we can compare over time and as much as possible measure the actual changes on the ground. The second key pillar that we see as part of performing large multi-temporal series analysis is what's known as ODC, or Open Data Cube. So you'll hear us talk about this, and there's a few slides coming up on that. The infrastructure that is required to store, query, and access data over large areas is something that's been the topic of much work in terms of creating new infrastructure. And we at PCI have basically adopted the use of the Open Data Cube, which is an initiative that was born out of the Australia Geoscience Group, to create this nice infrastructure that allows us to take our ARD data and store it in an Open Data Cube platform. And we'll go through some more slides on that in a minute. But for now, suffice it to say that once we produce these large volumes of ARD data, we need to put them somewhere to perform analysis. And we at PCI have chosen to adopt the Open Data Cube as a platform to do so. The third key pillar that we see for time series analysis is somewhere to perform multi-temporal analysis. So we need to query the data, we need tools, we need to prototype, and really this is currently possible in a few different ways. there are built-in algorithms in the Open Data Cube that allow you to perform multi-temporal analysis, and I'll show you a few examples of that in a minute. But also, even within the software that we produce with Geomatica, for example, with the Python interface, and even within the desktop tools, we could develop some algorithms, do some prototyping, and then deploy those on the multi-temporal data set. So if we think about producing ARD, typically this is more of a big data type of problem, either in terms of spatial coverage, so a large geospatial extent. And if we add the temporal element to that, so if we think of a large geospatial area over many, many years, so 20, 30 years of data that's been collected by some satellites in some cases, then that's a problem that's custom made for large volume production system, which is our GXL system. The Open Data Cube in the middle, as we see, and then on the right, multi-temporal analysis through Geomatica prototyping. So just to drill down a little bit more into some examples and why we would want to do this. So ARD tools allows you to do two things within our environment. If we simplify a little bit, precise alignment down to 1/10 of a pixel, and radiometric normalization. So here we see image alignment that's provided through a data provider. So in this case, I believe we're looking at Sentinel-2 data, and all three of these locations have been imaged multiple times by perhaps a different sensor or a different view angle. And you can see that there's shifts in the data. The linear features like the roads and the rivers are displaced in the data set. So we can actually deploy our technology within Geomatica or GXL, and we can bring this data into pixel perfect alignment, so down to 1/10 of a pixel. And that's going to be really important when you're measuring changes over time, because you want to be measuring actual changes on the ground, not changes in the registration errors in the data set. Another example here is just an animated sequence data that's been provided on the left from a data provider. And once we run that through our super registration algorithms, we can get down to 1/10 of a pixel and really, really minimize the shifting that's occurring between the different images. And that's really going to allow you to measure the location and the objects and the different features that are changing on the ground, as opposed to any registration errors. The second element that's key to ARD is radiometric normalization. So right now, I've got a few examples here of some data sets that have been collected by different satellites. In this case, we're looking at a PlanetScope image collected on December 1st, 2016. And then we have the exact same location collected 2 days later from a different sensor, from RapidEye. And without doing the proper calibration on the data, the radiometric normalization, many people right now are generating NDVI products. Maybe they're collecting the data in such a way, or the vendor might be providing the data in such a way that it can be used that way. But in many cases, some customers are maybe not doing the calibration properly. And so they go ahead and they produce information layers like NDVI, which is a normalized difference vegetation index, from that first image. And then they do the same thing on the second image. And it looks like there are quite a few changes on the ground. But really, that's just because the data has not been properly calibrated or normalized. The radiometric information has not been normalized to take into account atmospheric effects. So this picture is lying to us a little bit. It's not really telling us what's happening on the ground. So if we actually do the surface reflectance calibration and regenerate that NDVI product, which is what we've done in this case, we can see that first PlanetScope image, this NDVI map is really more reflective of what's occurring on the ground. And then if we go to the next image, we can see that really the changes are very, very subtle, and the location of the changes is actually very different from the non-calibrated data. So that's very important to calibrate data as you're performing multi-temporal analysis or performing any kind of analysis really that is meant to measure the actual information coming from the satellite. So within our offering, within the 2018 offering, we have a number of tools that we're making available to generate analysis-ready data. So we have a toolkit that consists of radiometrically calibrated data. We have some spectral classification algorithms. So those basically look at the channels within satellite images and pre-classify data sets based on existing algorithms that are built into the software. And those pre-classifications are going to be useful for further steps as we go to calibrate our data. Once we have some of these information products generated, we can go ahead and radiometrically correct the data to normalize it. And furthermore, we can do another step, which is quite unique and we think very important, which is to topographically normalize the data to remove sun angle effects in areas that have high topography. And I'll have an example of that in a minute. This is an example of a pre-classification. So we have a Landsat 8 image, and we currently have a natural color composite up on the screen. You can see different land cover like forest and water and lakes and built up areas and so on. So using the existing information in the image, so red, green, blue, NIR, shortwave infrared bands, we can actually generate an automatic pre-classification of this data to then be used for normalizing the data down along the ARD production chain. Just from an aesthetic point of view, doing this calibration is obviously, this atmospheric correction is obviously very beneficial just from an aesthetic point of view, as I pointed out. So if we look on the left, we have a top of atmosphere reflectance products that has not been atmospherically corrected. And if you look on the right, once we take into account the atmosphere, we actually get colors that are much more representative of the land cover on the ground. So just from a data mosaicing point of view, even aside from just doing analysis, performing atmospheric correction can have benefits as well. Topographic normalization is something I mentioned earlier, and really what this is very useful because in areas where you have a topography, if you can imagine the image on the left being collected multiple times over the course of a season, the sun angle will change from the spring to the summer. The extent of the shadows on the slopes will differ, and so that will affect the radiometry on the slopes. And so topographic normalization can take this into account. What you see on the right is a topographically normalized Landsat data set that has taken into account the slopes. So if we actually generate this data over time, this is really going to help us with our analysis to be able to generate better measurements. Just a few words on the data cube. I mentioned it earlier. I just wanted to, for those of you who are not familiar, this is an initiative that's really taking off, and it was born out of a very innovative group out of Australia known as Australian Geoscience. And basically what they did is they invested quite a bit of resources to create an infrastructure whereby they could download, store, and conduct analysis on every single Landsat image ever collected over the entire continent of Australia. So rather than store this in sort of like a traditional file-based system, they created a new infrastructure, which was known at the time as the Australian Data Cube. And what you see here is kind of a representation of the entire continent that's been stored for a period of 30 years. And so every single pixel that's ever been collected by Landsat is available through this data cube infrastructure. It has database components. It has a specific file format known as netcdf. And what this allows is efficient storage of the data, efficient querying of the data to really make this multi-temporal analysis possible. So all of this investment that was made in Australia has actually been made available to the global Earth observation community or anyone that wants to use it through an open source initiative. So they've open sourced the code, and the Committee on Earth Observation Systems, CEOS, has adopted the Australian Data Cube as the open data cube. So PCI is actively developing prototype data cube projects with some clients right now, and we'd be happy to talk to you some more about how to leverage this great architecture that's been created in Australia. These are some examples from that Australian data cube. This is quite an interesting product. So if we were trying to generate a minimum and a maximum tide extent map in a traditional sense, we would probably have to hope for a perfect imaging day when the tides are coincident with the orbits, for example. So that would be a very difficult thing to achieve over large areas. So rather than taking that approach, which would probably not yield the best results, this is an example of leveraging that deep temporal stack to look at the minimum and the maximum tidal extents. So where is the water present over time over this particular intertidal basin? And this can inform policy making for biodiversity studies, or this could be studied over time and is a useful piece of information that would be otherwise difficult to attain. Another example is flood mapping. So this is an example of a product that is looking at water observation from space. So it looks at the frequency and the location of water. And you can see that the only area where there's a permanent water body is this little tiny portion down in the bottom right side of this graphic. And everything else is only present some percentage of the time, some percentage of the observation period, going down to the red areas, which are very, very infrequent. But this, again, is an information product that could be very, very useful for policy making, for informing decisions. For example, if you're in an emergency management situation and you would like to know what the probability of flooding is going to be based on actual flooding having occurred in the past and within a certain river basins, this could be a very useful information product to have. And it's only possible to generate this information through the multi-temporal analysis. So I just want to show you quickly a gallery of results of some of the products that we've done for this type of analysis. So here what we have is a Landsat 8 image. And I just want to show you that this data set has actually been pan sharpened using a new algorithm that we've made available within our technology this year. Let me just shut my email off, sorry about that. So with this year, we've created a new pan sharpening algorithm known as MRA Fusion. So it's multi-resolution analysis fusion. And its goal is a little bit different from traditional pan sharpening algorithms. Its goal is to actually preserve the radiometry as much as possible to make the data suitable for analysis. So we've conducted studies and have compared the radiometry in the original data as compared to the pan sharpened data sets with the MRA fusion method, and we found that it preserves the radiometry to a high degree of fidelity as compared to other pan sharpening algorithms, even available within our software, for example, the UNB pan sharpening. So depending on what you're doing, if you're trying to produce a nice looking map and you want to then you might use the pan sharpening algorithm, the traditional pan sharpening within our software. But if you're to perform a scientific analysis for ARD or other types of analysis for science, then you would use the new MRA fusion algorithm. So this is just showing the Landsat data that's been improved in resolution. So it's down to 15 meters as opposed to the 30 meters, which is the multispectral resolution of Landsat. And then if we go to the pre-classification or the spectral classification, so here we have that same data set. And here what we've done is through a specific algorithm within our software known as spec class, we can actually generate this land use line cover classification with quite a few number of classes that are going to be useful. They could be useful for a number of reasons. So you might need the water bodies as a polygon layer to be automatically extracted. That would be a byproduct of this process. But in the context of atmospheric correction and topographic normalization, knowing the land cover and how to apply different parameters spatially in different areas is very important. So that was our reason for creating this spectral classification algorithm, and we'll use that as part of the ARD workflow down the road. Another key thing that we've added in is topographic normalization. So here we can see an area that has quite a bit of terrain. You can see there's some fairly rugged terrain in this particular image. And what we've done is we've actually mapped where the slopes are located, and we've identified the illumination angles, and we've taken into account the topography so that we can actually remove the topography and normalize the data. So you can see here, this data set is a little bit unusual to look at. It's harder to interpret because we don't see the mountains anymore, but it's actually much better when you're performing analysis because, as I said earlier, these shadows on these slopes are going to change over time depending on the illumination conditions based on the rotation of the Earth respective to the sun over the seasons. So this is something that's very, very important to do as we perform analysis on multi-temporal data sets. So I'm going to keep going on the next topic, which is aerial production. So aerial production is another key topic or a key area where we've developed technology within 2018. And here we have a list of algorithms or typical workflow, I guess, for aerial production. And this is really an area where PCI has spent a lot of time over the last, I would say, 4 or 5 years to streamline this workflow and not only improve the speed with which these information products can be generated, but really allow the user to control the quality of the products that are coming out. One of the key pieces of technology that's been made available in this version and in recent versions is a new DEM extraction technique known as semi-global matching. And we felt the need to develop that technology because data sets are just getting higher and higher resolution. And it was important to add that technology to our software. So DSM quality has the quality of the DSMs that we're able to generate. The fact that we can generate them actually at 1-to-1 resolution. So if you have a 6 centimeter aerial data set that has a very strong aero triangulation, or you can triangulate the data to be very, very accurate, you could extract the DSM at that same resolution as the native resolution of the data. And what that then makes possible is for you to project the orthos directly onto the DSM using a technique known as DSM True Ortho, which is going to be the subject of a detailed webinar coming up. And it's a very exciting technology that we're happy to be presenting to you. But in terms of the actual workflow, we spend a lot of time with customers around the world looking at what they're doing right now. And these are some of the technologies that they use. Typically, they don't use one specific package. They'll use multiple packages to do aerial production. And it's very common for either an external DEM or a DEM to be extracted from the stereo within the data. And then once that DEM is either used directly or extracted, clients typically generate ortho images, and then they inspect those orthos to see if there's any distortions due to problem areas in the DSM or the DTMs rather. And then they would make edits to the DEM, kind of regenerate the orthos and kind of go through this first cycle here until they reach a level where they're happy with the quality of the ortho images. Once they're happy with the ortho images, they then move to the next step, which is mosaicing. And they might inspect the initial cut lines and the color balancing, and then they'll do some edits to where the cut lines are located, or change the radiometry a little bit on some of the images to try to achieve that perfectly blended data set. And that's typically done through a process of QA and a cycle and so on. And external tools might be used here. DATM is an excellent piece of software for editing DMs. And Photoshop is obviously a great tool for making adjustments to images and so on. But those slow you down. You need to exit the workflow, work outside of a streamlined workflow, and then come back. So really, over the last 4 or 5 years, we've worked on this technology to make it easier and easier for customers to streamline their workflow. So if you look at this, this is basically the exact same workflow. The difference being there's no need to ever exit or rework data sets and regenerate products. Our whole philosophy with the aerial production tools is to dynamically render what the final product will look like to the user so they can make edits on the fly either to the DEM or to the color balancing before they generate the full product. So we really think this will save people time and allow them to achieve not only a faster product, but also a better quality product. So in the first sort of animated window here on the left, what you see is our ortho preview tool. So we can actually draw an area, and the software will render what the ortho will look like based on the DTM that's currently going to be used for the ortho generation process. Then we can make edits to that DTM over problem areas and make changes. Same thing with the color balancing. So the color balancing, we can actually edit cut lines, we can drop dodging points, we can adjust brightness and contrast, and even adjust specific colors to make everything blend as well as possible before the actual generation of the product. And then the final one, the touch-up side, this might be where people are using Photoshop right now. What you can actually do is you can stay within our environment and you can do things like basically re-establish contrast in saturated areas like this building here, which has a lot of bright response in red, green, blue, and that's saturating the final product. But we can actually draw a small polygon over this area, sample the statistics, retain the nice color balance within some of this external area, but then improve the contrast just over the saturated area. So, and we have lots of tools for doing that. So, but over and above that, above all these changes we made over the last few years, we have now the ability to perform multi-view digital surface model extraction. So you can, if you think of it this way, on the left, what you have are a series of digital surface models that have been extracted from individual pairs. And depending on the location of the camera with respect to the target on the ground and its elevation towards the camera, that will produce artifacts that can include occlusion areas or smearing, and basically these are undesirable artifacts that we need to remove. And typically the way that that's dealt with is you would remove the building, so you would filter the buildings off to generate a terrain model, a digital terrain model, and then you would project the image with some lean, and then you would basically have a product that is acceptable, but obviously suffers from some lean and occlusions in your resulting product. So because we have this semi-global matching DSM extraction capability at very high resolution, we can actually merge all of these different DSMs and produce a nadir looking DSM, which will remove occlusions and problem areas within the DSMs, which can then be transferred over to the DTM. So if we look at an example of that on the left, you have kind of the traditional ortho image that would be the process that you would use in that case is to remove surface features and produce a DTM, either from the stereo overlap or from a LiDAR data set. And then you would project the image and it would suffer from some occlusions and some building leans and so on. You can see that we can't see we can't see the other side of this building. And although it's nice that we can see all this side of this building, maybe it's not really what we want. We actually want to see what's behind it. And the location of the roof of this building is completely inaccurate as well. Whereas on the right, what we have is a projected DSM or true ortho product. And we don't have any occlusion areas, and we can see straight down on the sides of the building. So quite a nice final product. Also here, we have just a few more examples. So I'm just going to zoom in a little bit on some of these different buildings. You can see the building edges are nice and clean. The level of detail on the buildings themselves, the road surfaces are nice and smooth. The vegetation, the trees and so on are all nicely represented in this DSM that's been merged from multiple angles. And what that means is you can then generate an ortho product directly from the high quality DSM. So basically what we're able to generate is a DSM true ortho product from that data set. So this will be the subject of a detailed webinar coming up. We'll show you how to do this within our technology, and there'll be links to register for that webinar coming up. This is just another example of the reason why the DSM True Ortho is of such good quality, just the quality of the digital surface models that we're able to extract using our new semi-global matching techniques, which just keep getting faster and higher quality, is really what's driving this technology. I'm going to turn my attention now to the additional productivity and automation enhancements that we've added in our software. So we have, in this version, added the ability to not only work with optical data from an object-based image analysis point of view, but we've also added radar data. And radar data has been traditionally a little bit more difficult to work with on an object basis because radar data is inherently noisy. And if you think about the first thing that is always done with object-based image analysis, which is region growing or segmentation to create polygons based on homogeneous pixels, radar data is obviously very challenging to segmentation algorithms because of the noise that's inherent in the data, the speckle, and so on. So within our technology, with this release, what we've done is we've brought existing capabilities from within our suite directly into the image segmentation software. So what you would typically need to do is ingest your data. You would need to filter the data. You would want to remove some of the noise by performing a tail trim, and then you could try to segment the data, run a segmentation algorithm. So we take care of that for the user directly in the software. So you can point directly to a raw data product on file or a data set that's been ingested into our software package. And then once you've done that, you can apply filtering, tail trimming, and then depending on the type of data, we actually detect whether it's single polarized data, dual pole, or quad pole data within the software, and then we expose different things. So you'll see that in a minute. And based on what the data contains, we actually present the user with the opportunity to perform either texture analysis for dual pole data or full polarimetric analysis using quad pole data. And everything else is the same. So training site editing, classification, post-classification, everything else is basically the same. This is what the interface looks like now. You can see here that because I've chosen a fine beam, it looks like a RadarSat image, the system has detected that it's a quad pole data set, and it's exposed this SAR pre-process button. And what that button does is it then allows the user to specify what kind of adaptive filter to apply, what kind of tail trim percentage to apply, and that will then be used for the segmentation, which is exactly the same as previous versions of our software. So that can all be done automatically through the interface, so there's no need to run a whole bunch of pre-processing before bringing the data to Object Analyst. This will work directly off, for example, a raw RadarSat-2 image or a TerraSAR image. And you can see here the quality of the segmentation. So this is just an example of a RadarSat-2 quad pole data set over Alberta with some forestry areas and some river features, and all that we've changed here is the scale parameter, but the shape and compactness values are the same, and the filtering is the same, the tail trimming is the same. We get these nice homogeneous polygons that represent some of these different features in the image, such as cut blocks and forested areas and river bodies and so on. The attribute calculation, as I mentioned, is automatic, so we can basically detect that it's a quad pole data on the left, and then we expose all of these what are known as decompositions or polarimetric parameters, and we can add those to the polygons, which can then be used to train and classify the data sets using our supervised classification algorithms. In the case of dual pole data sets, you can see that the quad pole parameters are grayed out and only the SAR texture parameters are available in that situation. So the software is smart enough to detect what data you're working with and exposes only the parameters that you can successfully work with. Another thing that we've added, this goes for anything that you do within Object Analyst with 2018 going forward, is you can generate only segmentations over regions of interest. So you can either create a region of interest within our software, or you can use a vector polygon object from somewhere else, bring it in, and then you can just segment based on those areas. This is kind of a handy tool if you're just looking to experiment and see what the different parameters should be based on the data set that you're working with and what objects you're trying to classify. Another nice thing is the ground truth data that can be imported. So the ability to, if you are conducting field work or if you have point data from the field, you can basically bring that up as a point vector data set. And then the object analyst software will detect the location of those points respective to the polygons, and then you can assign those to specific classes. For example, probably in this case, it's a water polygon, and you can use that to train your algorithm automatically. So at this point, I'm going to pass to Jason for a run through of a demonstration data set that he's going to be working on a little bit later in a couple of weeks with RadarSat data.
Thank you, Kevin. Hello and welcome. My name is Jason Flatt. So just to give a brief teaser on the upcoming object-based SAR image analysis webinar we'll be hosting, I'd like to just showcase the data and the results we'll be generating. Now, this area that we're going to be working in is called Lac Saint-Pierre in Quebec, Canada, and it's an important piece of biodiversity as it contains numerous wetlands. And with this wealth of information, this can be used for scientists and policymakers for their further analysis. Now, for identifying wetlands, it's important that we have multi-temporal data as it can help identify the areas that are flooded during the spring and then vegetated during the summer. So for these data sets, we're going to leverage the RadarSat imagery and its full polarimetric, and it's collected between the spring and the summer. So just to showcase, we're going to be looking through this area of interest. We have one image captured in April when the area is flooded. We can zoom in, and then we can look at the July data as vegetation has grown over the flooded regions. Through the process, we're going to leverage all the new features available for object-based image analysis to identify and extract different types of land classes and wetlands in the region. Oh, yeah.
Great, thanks, Jason. As mentioned, that webinar is going to be occurring on December 11th, so I encourage you to register for that, and we'll be going through that in more detail. Okay, so I'm just going to tidy up a few things. We're getting near the end here. We have quite a few other improvements in our software for 2018. So specifically with respect to InSAR, we have added the ability to perform InSAR analysis using bistatic data. So if you think about TerraSAR X, which has a specific mission known as Tandem X, where both satellites are flying in a bistatic configuration, which is quite an advantageous configuration for reducing or improving the coherence within data sets, basically getting perfect coherence because the data sets are collected almost simultaneously. Another key thing that we've added is we've exposed some parameters for the phase unwrapping, so tiling the data set, the interferograms, so that the phase unwrapping can be a little bit more efficient. We have some filtering on the interferograms, once again, to make the phase unwrapping more efficient. We have a new algorithm known as the modified Goldstein filter. And we keep improving the positional registration part of our InSAR workflow. So that's quite useful for InSAR, but also for things like coherent change detection or anything where you're trying to compare radar images over time. Just thought I would show you a quick sample of a DEM that we extracted successfully using our bistatic InSAR workflow. This is a Tandem X data set over a mine site. And as you can see, this is quite a nice data set. It's a 1 meter ground sample distance data set that's been extracted from radar data. So very, very nice data that can be extracted from radar data. This is just an example of why the modified Goldstein filter really helps with the phase unwrapping. You can see on the right, the amount of noise in the interferograms is greatly reduced, which helps the phase unwrapping algorithm to more efficiently process data and resolve the phase unwrapping within data sets. Other areas where we've improved, and that will be the topic of, oh, but by the way, there will be a detailed drill down webinar on InSAR, which is why we mention it. And then Mosaic tool is another area of our software that we've improved and that has changed quite a bit with the 2018 version. Essentially, the Mosaic tool is now a separate independent tool available within our software. And it's quite a nice tool that can be used not only to generate mosaics that have been triangulated or corrected within Geomatica, but also data sets that maybe have been previously ortho-rectified externally and you wish to bring them together at a common resolution, common projection. You can bring existing orthos to the Mosaic tool now without doing any math modeling and produce mosaics, perfectly color balanced mosaics within this new Mosaic tool. So we'll be doing a detailed drill down on this in a future webinar. We always add sensor updates to our software. These are just some examples of some of the new sensor updates that we've added in. I encourage you to visit our website. We have a detailed, dedicated page where we keep track of the support that we have for the different sensors, which we do keep up to date, and also the what's new documentation for 2018 will give you the information for what sensors are supported and to what level of processing we can support the data. Specific updates to radar sensors, strip map for Sentinel, ALOS, and RISAT, SLC Spotlight, and bistatic, as mentioned already. One last thing to mention. So if you haven't understood this by now, basically the technology that we develop for all of our software is the concept that we have is to develop it to be available across our platform. And our platform includes a tool that we don't often talk about, but it's a very important tool that's used by quite a few of our clients. And it's a GXL, so it's a large volume production system. It can be used for making many different products. Traditionally, PCI customers have used it to produce very, very large mosaics over large areas like countrywide mosaics. But in the context of ARD, which is a emerging topic and an area where we're focusing a lot of our attention, GXL is definitely a great tool for processing large data sets to produce ARD data sets. So every time we add all of the technology that we've talked about has been implemented in some fashion in workflows within GXL. So we add new modules, we improve the interface, we improve the performance. Specific to GXL, we've added ADS push broom, which is an aerial push broom scanner. We've added a specific ADS functionality within 2018, and all of the sensor updates that we put in as well are there. So we really add in quite a bit, and GXL is a key tool that benefits from all of this technology that we develop on a continual basis. So I just want to remind you of the upcoming webinar. I'm just going to copy the link and pass it to you via the chat. So Jason gave you a little bit of a quick description there on what was coming, and I'll just send this out here. So I just sent everyone in the webinar the link to register for the next webinar, which is going to be focused on multi-temporal wetland mapping using RADARSAT-2 data and SAR object-based image analysis. So that'll be the next one. And then we're also going to drill deep into DSM true ortho, InSAR processing, multi-sensor mosaicing, and analysis-ready data tools for multi-temporal analysis. So with that, I'm going to open the floor for questions. And if you haven't already typed in your questions, we encourage you to do so now. We would be happy to answer any questions you have. So just going to open up the question panel and have a look. And it looks like there's a question about creating data sets at different resolutions and where the sources are different. So that's a very important concept. So a lot of analysis that's being done right now with multi-temporal analysis tends to be focused on one particular sensor, Landsat being the most obvious. But really where we see the benefits would be to fill in some of the gaps in the coverage. As we all know, Landsat collects at a fixed orbit. And so maybe commercial satellites have been collected on a more frequent cycle. So within our technology, we have the vision to allow people to integrate multiple sensors. And we've done some of that work already in terms of cross-calibrating different sensors and normalizing the data and dealing with data at different resolutions. So that's a very important question. It's a very good question that this particular person asked, and it's definitely an area that we are working on. So we have a question about ARD workflow. So what type of extension do we need for the ARD workflow for multi-temporal analysis, radiometric normalization, and image alignment? And that's a great question. So there is technology within Geomatica right now that can help you get there. However, we've added specific algorithms that form a new module known as ARD. So we have an ARD specific module that needs to be added on to allow you to perform the analysis ready data processing. So if you're interested to find out more about that, just get in touch with us and we'll provide you the information you need. We have a question about whether we will support Sentinel-2 correction from TOA. I'm just trying to read TOA and BOA surface reflectance. So we are supporting Sentinel-2 data already in our software, and we can definitely perform this type of analysis. So top of atmosphere, bottom of atmosphere, that is possible right now within the software, and is definitely a capability that can be done. We have just a question that just came in about the difference between true ortho and DSM ortho. So what is the difference between true ortho and DSM ortho? Really, there isn't any difference. Well, I guess to explain it in a little bit more detail, the true ortho component of the DSM true ortho is using all of those different view angles to fill occlusion areas. So if you think about producing an ortho image from merged DSMs, then unless you take into account the occluded areas in the different DSM pairs, then you'll end up with some data voids. And so the true ortho component of that is mapping the location of those occlusions and then identifying the right data sets to fill in those occluded areas. So we'll be going into a lot of detail on DSM true ortho in the future webinar, and I encourage you to come back and watch that. Should be very interesting. Just looking if there's any more questions here. So we have a question about drones. So what information generated from drones? I guess the question is just related to what are we doing with respect to drones? So we continue to improve our technology, which means that we can support image processing for drone imagery. It's not the same approach as some of the other software that's out there that does structure from motion, which is very, very tolerant for I would call it consumer level drone imagery, like from DJI and so on. So we have actually processed a lot of drone data to produce quite a nice product. The starting point for us is we need to basically start from some location in terms of the aero triangulation. So once we have initial aero triangulation, which we can derive ourselves, or we can use some level of aero triangulation, we can really improve the triangulation and then generate quite a nice product. We have examples of that where we've processed even DJI data successfully. Yeah, so those are most of the questions. Just looking. There's a question about vertical accuracy of the 1 meter bistatic DM. I don't have the specifics on that, but I can follow up with the person that's asking this question. We have done some absolute validation studies with ground control with a lot of our DM generation technology. So we'd be happy to share that. And if we have published papers on that, I'll be happy to point this particular person to that information. So with that, I'd like to thank you once again for attending the webinar. And thank you for those of you who asked us some questions, and just encourage you once again to register for the next webinar in a couple of weeks, December 11th. We hope to see you there. Thanks very much.